Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I'd like to continue going through Chapter 6.2, looking at linear systems of differential equations with real eigenvalues. In our last video, we concluded with an example that started on page 8 of our guided lecture notes. It had the system of equations given by this matrix equation. And we saw that our phase portrait looked something like this. Sometimes we refer to this phase portrait as representing a sink, as solutions will always tend to go towards the origin. In our previous examples, we looked at another matrix equation where solutions tended to go away from the origin. And because of this behavior, we sometimes refer to this as a source. In the example previous to that one, our phase portrait looked more like this. And because of the nature of this, this is sometimes referred to as a saddle. I'm trying to imagine if you were if the red lines represented, directions to the horse's legs, you could be sitting as a person on the saddle right here. So here would be your body and one of your legs and another leg. So this looks kind of like a saddle. So now I'd like to finish going through a couple of more examples I have for you. If we could turn to page 10 of our guided lecture notes, then let's look at a couple more examples. Here we're asked to consider the linear system represented by this matrix equation, which has eigenvalues and eigenvectors shown here. And here I've decided to abbreviate how much work we have to do and do a lot of the work for us. So I first show how I'm looking for the eigenvalues by using the trace determinant approach. Again, recall that your trace is the sum of the entries on your main diagonal. So here your trace of your matrix A is 6, and the determinant of your matrix A is 9. So minus 6 lambda plus 9. This leads us to get a single eigenvalue of 3. And for our single eigenvalue, we now want to go look for our eigenvector, using the equation a minus lambda I x equals 0. Now again, notice when you subtract 3 off your main diagonal, you get the matrix of zeros. Now what this tells us is every non-zero vector is an eigenvector. Remember, we're looking for non-trivial vectors that when you multiply by this, you get the zero vector back. But it tells us because you're having a matrix of zeros, every vector is an eigenvector. Every non-zero eigenvector is a eigenvector. However, I need 2. So for simplicity, let's grab 2 vectors. And I'm going to grab the 2 easiest ones I can think of. 1, 0 and 0, 1. And I'm going to take these to be 2 eigenvectors. And notice that they are linearly independent. From this, we can now write our general solution. Here our general solution will look like x of t, c1e to the 3t times its eigenvector, c2e to the 3t times its eigenvector. Notice that when I write these, that we did not include that extra factor of t like we had done in previous problems. It's because these two solutions are not multiples of each other. These are linearly independent solutions. And this now gives us our general solution. Now, I really wanted to focus on this example in the phase portrait because there's lots of different ideas of what your phase portrait could look like. And if you haven't done so, you might want to refer back to one of the notes I made earlier, where I encourage you to go and look at the two supplements I provided for you. One referred to as the introduction to the phase plane and one as the trace determinant plane. These will give you a great look at all the different outcomes these phase portraits could look like. So in this example, we want to look at what happens when your phase portrait, what happens to your phase portrait when every vector is an eigenvector. This is a different outcome. And so we want to really explore this scenario. So let's start by drawing your phase portrait. Draw your coordinate system. Label it y and x. And let's start with our two eigenvectors that we chose, 0, 1, and 1, 0. 0, 1, 0 would be an eigenvector that's associated with the x-axis. The second one, 0, 1, will be associated with the y-axis. And notice that because our eigenvalue is 3 on both of these, solutions are going to tend to move away from the origin. But we picked these two vectors by chance. Remember, every vector was an eigenvector, so we could have picked any other vectors. I just like these ones for simplicity. Also notice that these two vectors, their eigenvalues are the same, which means if you're thinking in terms of vectors moving in the plane, neither of these has a stronger pull than the other. So that if we started with an initial condition that was anywhere in the plane, it would be influenced by these two solutions, but they'd be influenced equally. This would produce a series of straight lines always emanating from the origin. I'm drawing the best straight lines I can on my tablet. These are supposed to be straight though. Every vector is an eigenvector, or every solution moves outward from the origin with no curvature. Because of the nature of what this looks like, this is sometimes referred to as a starburst source. Imagine a star exploding and everything moving outwards. Again, I really think you should look at the introduction to the phase plane and the trace determinant plane supplements to get an overview of what these might look like. And maybe also what would consider what would happen if the eigenvalue were not 3 but -3. Then what would this portrait look like? I'll leave that for you to consider and to refer to those supplements to help you with that. Okay, I hope this is helpful. Let's look at another example. Consider the linear system given by this matrix equation. And again, I'd like to be able to look at the eigenvalues and the eigenvectors. And to help you, I've produced these for us already. Using the trace determinant approach, your eigenvalues can be found by looking at the polynomial lambda squared minus the trace of a plus your determinant. Remember, the trace of your matrix is always going to be the sum of that main diagonal. So here the trace of your matrix A is equal to -5, and the determinant of your matrix A is going to be 4 minus 4, which is 0. So we'll include our trace and our determinant. Notice that our polynomial is factorable, and we get two solutions, two different eigenvalues, 0 and -5. If our eigenvalue is 0, then we're subtracting 0 off of the main diagonal, which leaves our original matrix. And I still want to be able to grab an eigenvector out of this. So let's say our first eigenvector, well, there's an infinite that I could choose, but what if we chose 1 of the first column and 2 of the second column? That would work. For our eigenvalue of -5, we're subtracting 5 off the main diagonal. But since we're subtracting off -5, we end up adding 5, and we get this matrix. And here we seek another eigenvector. Here we could use the eigenvector maybe 2, -1. And because we have two eigenvectors, we can write our general solution. As x of t, c1e to the 0t times its eigenvector 1, 2 plus c2e to the -5t times its eigenvector. It feels weird writing this with a 0 exponent though. So I feel like I want to rewrite this still. And maybe write it as x of t as just c1 times our vector 1, 2 plus c2e to the -5t times 2, -1. Now, regardless which way you write your solution, I kind of feel like the second one is a nicer form for our solution. But technically, both of these are correct. Okay, and now let's proceed and write our phase portrait. And what I'm trying to do in these examples now is to give you a good idea of all the different outcomes you might expect to see for what these phase portraits could look like. And let's start by drawing our eigenvectors again. So one of our eigenvectors, 1, 2, goes 1 in the x direction and 2 in the y direction. It goes through this point. But I'm going to draw an entire line through that point. And this is associated with the eigenvalue 0. Our second eigenvector will go through the point 2, -1. So 2 to the right, 1 down, it'll go through this point. Okay, so let's now draw a line through our second point. And let's label it with its eigenvalue. Let's think about the directions now. When your eigenvalue is -5, it tells us that as time goes on, e to the -5t shrinks. And so that any initial condition on this line will shrink and move towards the origin. However, if your eigenvalue is 0, then there is no movement on this line. Any initial condition or initial point you start on stays at that point. There is no movement at all. So now let's consider what would happen to initial conditions that started somewhere else not on one of these lines. And what you want to notice, if you started here, the only movement that you see is because of the movement that is being pulled by this eigenvalue -5. And so solutions would move parallel to it. And actually, any solution would move parallel to that line until it crashes into the other eigenvector. So our phase portrait here looks like a series of straight lines that move parallel to the eigenvector with the eigenvalue -5. And then when they hit the other line where there is no movement, they just stop. Okay. I hope this is helpful and it gives you a good look at the different phase portraits you might expect to see. But again, if you haven't done so, I really think that you should go and look back at the other two supplements that I've created, the Introduction to the Phase Plane and your Trace Determinant Plane in our Canvas course. This will give you a good look at what other outcomes you might expect to see. Okay. I have one more item to discuss with you. It talks about creating a generalized eigenvector for a system with insufficient eigenvectors. However, I'm going to do this in a separate video, and so I'll see you back here in a little bit.